inaugural Discover Mini-symposium series organized by the Michigan Institute for Computational Discovery and Engineering, or MICDE. And this time, the title is Women in Computational Science, where you can learn about the power of diversity and innovation in computational science and engineering, providing an opportunity for you to learn about the groundbreaking research of women scientists. So today we have Catherine Heitman from the Argonne National Laboratory. We have Liz Livingston, the Claire Booth Lewis Fellowship winner, and Rachel Neimer from the Women in Science and Engineering here at University of Michigan. And the event will finish with a panel discussion where you'll be able to ask questions and discover more about the challenges and that women researchers have in various stages of their career and working in different branches. So without further ado, I want to welcome Sarah McNeid, the MICDE's academic program coordinator and our DEI lead, to introduce the first speaker.
Thank you, Pancho. So Liz Livingston is a PhD candidate in mechanical engineering and scientific computing here at the University of Michigan. She was selected as a Claire Booth Luce Graduate Fellow in 2019. MICDE has administered the Claire Booth Luce Graduate Fellowship at U of M, which was created with the goal of increasing the participation of women in the sciences, mathematics, and engineering. Liz's research is at the intersection of computational sciences and biomechanics, and she earned her master's and bachelor's degrees in mechanical engineering from the University of Illinois at Urbana-Champaign. Thank you.
Thank you for the introduction. Hopefully this is working. So my PhD research is focused on discovering mathematical models for systems, and in particular, biological systems. So I'm personally interested in biological systems and more at the whole scale body, so not necessarily down at the cellular or biomechanical level, and also focused on more fluid and solid mechanics systems within the body. So one example of a biological system that I look into is blood flow through arteries, in particular the coronary arteries, the vessels around the heart. We've also in our group looked at brain growth and folding in fetal brain development, and then also in ligament strain and tissue damage. So for each one of these biological systems, there are different observables or data that you can gather from that system. And in the case of all biological systems, you have some imaging modality that you might be able to use to collect the geometry. So the coronary geometry, the brain geometry, or the ligament geometry. You can also estimate the material composition when compared to previous experimental results. And in the case of blood flow, there are methods of gathering the flow or the pressure through invasive measurements. And then for tissues like the brain and ligament, you can also estimate the displacement field using these different imaging techniques. So once you have that data, you also want to model some sort of phenomena for this system using a governing equation. In the case of the blood flow through arteries, you can use the Navier-Stokes equations. And in the brain and ligament cases, you can use linear momentum balance. And in the brain problem, we also have an additional state variable to model the growth of the braiding. So why do we care about being able to model these systems, these biological systems? Well, in patient care, if you have a computational model, you might be able to improve physicians' decision-making capabilities in surgery planning, and then also real-time decision-making in the clinic. In improvements in imaging and computation have improved greatly over the last century. In imaging, we've gone from simple X-ray imaging all the way up to MRI and the capability to get 3D pictures of the internal tissues. And in computation, we've gone from, again, nothing simple electrical logic gates all the way up to supercomputers and now personal computers that are as powerful as those original supercomputers. So these improvements in imaging, and that is the improvement in data collection and the improvements in computation, means that we can have increasingly complex models. So we can look at multi-scale, multi-physics, high fidelity simulations of biological systems. But a caveat to that is that the data that you collect, MRI is very sophisticated, but you are still limited in what you can actually observe in vivo in a live human. And then in terms of complex models, if you're using a supercomputer to produce some sort of high fidelity simulation, that isn't necessarily useful for a physician. So we want to be able to produce some sort of reduced order or surrogate models that will still maintain a high level of accuracy for physicians to use. So in general, we care about the interpretability of our model for that biological system. And we care about that from a mathematical standpoint, because we want to be able to write down the terms that affect the model. And then we care about it from the clinical standpoint, because if you know those terms, then you also understand the parameters that affect that system. And so there are a couple of different approaches that we can use to get to these new reduced order or surrogate models. And the first is analytically. So if you start with those governing equations I showed on the first slide, you can apply a series of successive approximations and come to some sort of analytically based reduced order model. This can be difficult to derive, but of course it's going to be a lot easier to solve and a lot faster than the full order model, the FOM. And existing work is really just any way that you choose to reduce the order of your system, from 3D to 1D flow, 3D to 1D solid mechanics, anything. Another approach would be to look at a semi-analytic reduced order model, where you infer the parameters of the system. So you estimate the parameters. And in this approach, it's still interpretable. You still see the actual equation of the system. It's still based on physics, and therefore it must be accurate. But it can be difficult to develop these approaches. And then also, there is a body of existing work, system identification for nonlinear dynamics from Steve Brunton and Nathan Kutz. And then there's also been a wave of variational approaches from our lab group and from other lab groups with variational system inference, weak SIMD, derivative-based SIMD. Finally, you can have a surrogate model. So this is a model like a neural network where you're just approximating the function. You take an input, you map it to an output using some training data. Of course, once you have this surrogate model, it's very fast. But one caveat is that it's only accurate within the training data that you used. So it's also much easier to train than derive compared to an analytic or semi-analytic approach. And of course, there's a huge body of work for neural networks, but we're particularly interested in partial differential equations on neural networks. And so we look at physics-informed neural networks, DeepONet, deep Green's function, and other works. So first, we'll start with an analytic reduced order model. We can start with the case of flow. So as mentioned before, you can start with 3D as your high fidelity model, your full order model. And even with this 3D model, you still have a set of assumptions. So you're still starting with assuming a continuum, Newtonian, viscous, incompressible fluid. We're also considering it at steady state. And even with all those assumptions applied, this is still considered our full order or high fidelity model. We have the continuity and momentum balance equations for this model, and the variables that we're solving for are the 3D velocity and pressure. Then we can look at the successive approximations. In this case, we'll start with axisymmetry. So when we do that, we'll consider cylindrical coordinates. We remove that theta component, and then you get down to the 2D velocity, UR and UZ. So we've reduced the order, but maybe not enough for use in clinical scenarios. So you can take it one step further, take all those 2D assumptions, and then also assume the velocity and pressure is averaged over the cross-section. And then you also assume a specific shape of the axial velocity profile, UZ of R. And when you do that, you get all the way down to a single velocity component that you're solving for, as well as the pressure. So we have this existing 1D model. It works fairly well, but of course, and it's much faster because you're going from 3D to 1D. It's much easier to solve these equations. But with this reduction in order, you've also lost some of the accuracy. You've made assumptions, you know what those assumptions are, and so you're not going to be able to model different clinical scenarios. So in terms of clinical scenarios, what do we actually care about? Come on, there we go. So a metric that doctors use is called the fractional flow reserve. And when they do this, they have a pressure catheter that they push through an obstruction or a stenosis, and they measure the pressure after that stenosis relative to the unobstructed pressure before or proximal to the stenosis. So this is a functional metric of the degree of flow obstruction in a vessel, and it's been shown to be very effective to help doctors in making decisions, but it's an invasive procedure, and so it poses a high risk to the patient. So we want to replace this metric computationally, and so we want to improve that existing 1D model that we have. And to do that, we'll start from the same place. We start from our 2D model. We have incompressible Navier-Stokes with axisymmetric assumptions and in cylindrical coordinates. if you take the continuity and conservation of momentum equation and put them together, take area averaging and then integrate over your domain, then you can arrive at this form for the pressure gradient in a vessel. And then the next assumption that we made in the last model was an exact form of the velocity profile. Instead of doing that, we're going to say that the axial velocity is a separable function of z and r. And r here in our WR function is actually the normalized velocity r hat. When you take that assumption, you need to know what those functions are. So we get wz from our momentum balance equation, shifting the terms around. And then we actually do still assume a form for WR. In this case, we assume a polynomial form, but with an unknown coefficient out AI. When you plug that in, you can simplify and get down to what we call the separation of variables model. And in this model, I'd just like to point out that we have two unknown coefficients, gamma 1 and gamma 2. And these coefficients are not derived analytically. We're going to find them from data. So we run a bunch of high fidelity 3D simulations, and then we use those simulations to estimate those coefficients for the model. So once we do that, we can run it on a set of test data. On the left here, we have the pressure gradient along a certain vessel with a single obstruction. And then on the right, we have a more severe obstruction. In both cases, you can see the CFD results in black, and then you can see the separation of variables model in the blue dashed line. And you can see that on the left, where we know that separation of variables should apply, we have a pretty close fit to our CFD results. But on the right, where we didn't expect it to apply, we have a very severe restriction. We have a closeness in terms of the capturing the curvature, but we start to lose the fit in the tightest portion of the stenosis and in the distal section. We can also go beyond our training data and apply two stenoses. And because our assumptions had nothing to do with the geometry of the vessel, we get just as good of a fit even with two stenoses in the geometry. And in terms of what the separation of variables actually mean, if you look on the left, this is the vessel in black outlined here, and then this is the normalized velocity profiles. And you can see that they don't really change in shape along the vessel. The areas where we lose our fit compared to the CFD, you can see a slight change in that velocity profile. And then in the case where we didn't expect it to fit, you can see a relatively large change in the velocity profile right inside that stenosis and in the diverging section. So we have a pretty good model, and it even performs well in cases where we didn't expect it to perform well, but we do still want a better reduced order model. So how do we do that? Once again, we go back to our incompressible Navier-Stokes with axisymmetric conditions, this equation once again for the pressure gradient, and then we start relaxing our assumptions about that velocity profile. So instead of having a separable function, we consider a tensor basis for u z of r. So in this case, we have our unknown coefficient aij, we have our polynomial again, ri, but then we have this unknown basis function fj of z. So when you plug this in, you get a similar model with 4 terms, but in this case, in our first term, we have a nonlinear combination of coefficients, which is going to make it much more difficult to find what those coefficients are from the data. And then we also have this undefined basis fj of z. So taking some preliminary results, looking at this model, we just considered a cosine function as our basis just to start. So with this cosine function, you increase the size of that basis, j from 2, 4, and 8, and you can see we start to get a better and better fit to our data. But then going from 8 to 16, you can see that we start to have diminishing returns in terms of the ability to fit the data with this model. So what this is telling us is that there's a limited expressivity in the coefficients, in these nonlinear coefficients. And so we want to explore alternative options for producing reduced order models or surrogate modeling approaches. So that brings us to the next type of model that we might use, which is a semi-analytic reduced order model, so system inference. So how does system inference work? Instead of starting from the governing equations, we start from the physical system, and it can be solid or fluid mechanics. From that system, we can collect some sort of data. Then this will be measured from the system. We can take the displacement or the flow, and then using that data, we can estimate the governing equation. And this will be informed based on other differential equations. And we usually could do this in the strong form. We can also do this in the weak form. And in the weak form, you might have some benefits like being able to see the boundary conditions that appear naturally. And then you also have a choice of basis functions that will allow a continuous representation, even from discrete data. So with this framework, what are we interested in looking at? I'm going to shift problems a little bit here from blood flow. So in general, we can look at fracture in materials. In biological systems, we could look at fracture in bone, we could look at fracture in ligaments, and then you can also look at fracture in vessels, in blood flow, in intimal tears. So in traditional fracture mechanics, you typically model a crack as a discontinuity in your material, and that can be very computationally expensive. And so there's a technique of phase field fracture modeling, where you model the damage as a scalar field. So D equal to 0 is an undamaged material, D equals to 1 is the damaged state. And then when you have that phase field representation of damage, you can model the entire continuous object, and that damage field is also smoothed out, as you can see here in the figure on the right. So what equations do we actually work with in phase field fracture? We start with the inspiration from Griffith's fracture theory, and we look at the quasi-static crack evolution reformulated as an energy minimization problem, where fracture dynamics is a combination of the bulk energy in the damaged material and the surface energy of the crack. So using this approach, we then look at the equilibrium condition, and when you apply that equilibrium, you get to the Euler-Lagrange equations. And then once you have the Euler-Lagrange equations, they form a system of PDEs, and the solution to that system are the stationary points of the total energy functional. And the evolution of the crack, which is what we're interested in modeling, is governed by an additional differential equation, which is the gradient flow. So we combine these two equations together, and we can develop the weak formulation. And the weak formulation requires an additional term here, which is the history term. And that enforces the irreversibility of damage. So we don't have healing in our material. So with this residual, we have a couple of equations or functions here that are highlighted. And these functions are different options or choices in different phase field fracture approaches in the literature. So we have G of D, which is the degradation function. That's in the bulk energy. We have F of D, which is the geometric crack function, which is in the surface energy of the crack. And then we have D squiggle, which is a component of our history function. So from the literature, you can look at all the different options that people have used. This is just a table of some of the examples in the literature of different degradation, geometric, and history functions. So what we're interested in is system inference. So we look at first the residual, then we look at the functions that can vary. So in this case, we have the elasticity residual. The only function that can vary in this formulation is that degradation function. We then consider a linear combination of those degradation functions, and you can get the resulting constrained linear minimization problem. So you can do the same thing. Once you've discovered that degradation function, you look at the damage residual, and then you look at the differences in geometric crack functions and history functions. And we can get the second minimization problem for the coefficients beta and zeta. In this case, I want to point out that beta naught comes from the damage evolution coefficient, and the zetas are the coefficients of our different history functions. So the goal of these algebraic minimization schemes is to solve for those coefficients. In the first problem, solve for the coefficients alpha. In the second problem, the coefficients beta and zeta. So taking a step back and looking at that table of all the different options, we can run a little test case. We'll look at quadratic and quasi-quadratic degradation, linear and single well, geometric, and then a single history function. So in order to do this system inference approach, we have to have some forward data. So in that forward data, we hold the geometric function and history function steady, and we have our two different degradation functions. Here you can see the effect of the degradation function on the load strain curve. And then we have some of the propagation of the damage. And you can see in the top figure here, these results that I'm showing are not quite time-resolved results. It's not a fine enough time step. So these oscillations that you're seeing are not from the degradation function. It's from the simulation quality. But that's good enough for our inference problem. So our inference problem, again, is solving for the alpha coefficients. In this case, we only have 2. And we start with some initial guess. They have to sum to 1. So Our initial guess is 0.5. And in this first problem, you can see that the discovered solution was 1 and 0 when we knew that that was the exact result, and then the same thing in the second problem. So then we can look at varying the geometric function. So in this case, we hold steady with a quasi-quadratic degradation function, and we vary that geometric function. So we have single well and double well for our geometric crack function. So once again, you can see the way that this affects the damage propagation in the material, in this case with slightly better time resolution. And when you look at the inference problem, in this case, we're solving for our betas and our zetas. Because I only have a single history function, we're really just solving for what zeta is. We're not identifying which history function. But you can see here, it might be a little bit difficult to see the numbers, but we are capturing the correct beta naught, which is just the coefficient in our damage evolution. And we are able to eliminate beta 1 and beta 2 in this first problem. And in the second problem, we were successful in eliminating beta 1 and beta 2. I shouldn't say eliminating, finding that they come close to 0. And also we do capture close to the correct zeta coefficient. So that's an approach to system inference with semi-analytic reduced order model. And finally, I want to talk about surrogate modeling or functional approximation using neural networks. So in general, with surrogate modeling, you're mapping some sort of input to an output, and it's just an approximation of the function. That's a traditional neural network. There's a wave of approaches where we actually model the PDE in a neural network. There's a lot of different ways to approach this problem, but some of them are listed here, and a little schematic on the right is of PINs, physics-informed neural networks. And the key limitation to all these approaches is that they only work on structured data. And so in our group, to resolve this issue, we have a technique called graph calculus, or specifically non-local calculus on finite weighted graphs. We can combine this with neural networks, and then we have what we call graph calculus neural networks. So first, a little bit of mechanics. What is graph calculus? So, come on, here we go. In the past, finite difference and kernel approaches have been used to define derivatives on graphs, and we've formalized these methods in terms of a non-local calculus on graphs. So up here, this reference is one of the papers that we used in this derivation from Gilbo and Osher. So with this method, we can approximate the non-local derivatives up to a certain arbitrary precision in the same way that we can in finite difference methods. And these non-local derivatives are consistent with the corresponding local derivative up to a desired order of accuracy. So what you're seeing here, the notation here is for the non-local derivative. And then in this error, the accuracy that we're reaching, we have the non-local derivative with the corresponding local derivative. So using this non-local calculus, we can work on unstructured data. And then how do we actually combine that with a neural network? We start with some sort of input. We have phi1, phi2, and then we can apply those kernels that we defined in our non-local calculus. So in this case, we have operators for del x1, del x2, and an identity operation. And we do this on both of our inputs, and then you have your derivatives inside of your neural network. And then you can apply a regular neural network operation where you multiply by the weights and apply an activation function. Do this as many times as you want and map to your output. And in this way, we've extended our graph convolution networks to use kernels that are defined by non-local calculus with gcalc NN. So a little show of how this works. Instead of jumping to a biological problem, we'll start with a simple PDE, linear advection, so du dt equals negative c du dx plus du dt, du dy on a unit square. And we picked this because it has an exact solution. It's a simple first order linear PDE. And we picked a wave speed of 1/2. And the first thing that we wanted to do is prove that we could represent this PDE in this neural network structure. And so we played around with how much data do we really need in order to represent that PDE. So here we show the training loss for the neural network for increasing sizes from 5x5 to 10x10 to 15x15. And then you can see the parity. So on the this is showing ground truth to prediction of the neural network on the testing data set. And you can see that as you increase the amount of data on a graph, it improves the parity and the representation of that data. So what do we ultimately want to be able to do with this? We want to be able to actually solve the PDE. And in this case, we want to be able to propagate the solution forward in time. So in all, their ultimate goal of my PhD work is to not just generate more high fidelity advanced simulations, but to provide a deeper understanding of the systems that we're modeling. There's a bunch of different techniques that we can use to do this. There's analytically based reduced order models, semi-analytic reduced order models, and then of course, surrogate models like neural networks. And with the work that we have, in terms of fluid flow, we want to apply the system inference techniques to fluid flow. There's another postdoc in my lab group who's already done some surrogate modeling of fluid flow. So that's out of my work, scope of my work. Also in the inference problem, the results that I showed were for a nonlinear material, but it was for a nonlinear metal. So we want to apply that to a biological tissue like ligaments or tendons. And then in terms of the graph calc neural network, we want to actually implement that propagation to be able to solve the PDE. I'd like to thank my advisors and Sid Srivastava for dealing with all my presentation preparation and work in general. Thank you.
During the break. We have a break. So if anybody has any questions.
I have a few questions that I'll talk to during the break. I guess, you talked about the several different techniques. What's your thesis going to look like overall? I mean, is it going to be just kind of little pieces of vignettes in these three different areas, or do you have kind of a theme that connects?
The theme that I'm trying to make connect all of them is the biological system theme. So that's why I said I want the inference techniques for specifically for phase 4 biological systems. And then the graph calculus, we hope to apply to both of those systems as well, because it's more general.
You didn't really have time to talk about ligaments.
Yeah.
Ligaments are the applications in the other spaces, but I'd like to hear that at some point, because I tore a ligament about 6 months ago.
Yeah, one of my ideas was to include my brain scan and my ligament scan from when I tore my ACL. Yeah,
Okay.
That's why I'm motivated by biological systems.
Good.
It's just data to differential equations, right? So starting data-driven modeling methods specifically for biological systems. So yeah.
Sorry.
Go ahead.
So I had a short question about the data-driven models. You said that some of the ways you get data, it doesn't really, in vivo, in the kinds of scanning, it gives you only say 2-dimensional, while your actual problem is 3-dimensional. So how do you I don't know, so can you briefly say what you do to make that, what aspects of the model do you project the data into the 2-dimensional space, or do you try to do some forward modeling?
So there's a lot of work in that space. So with like the fluid problem, there was a whole another PhD from another student, and her work was completely on reconstructing the 3D geometry from these 2D images. And then some other work on that was reconstructing the estimation of flow for the boundary conditions of your simulation from these 2-dimensional images that you get of flow. So there is work on trying to project up. But then I think also the benefit of these reduced order models is if you get 2D data, then you could potentially run a reduced order forward model on lower dimension, and you would know what assumptions you're making in order to use that data in a 2D way. But it always depends on the problem and where you're getting your data from. Because in the phase field case, I talked about that damage phase field, and there isn't really a way to get the damage from a patient from an scan. So that's a whole nother problem of how do you actually get that phase field variable to be able to run this inference problem. So yeah.
So you mentioned potentially handing things like this off to a clinician. So what needs to happen between what you've done and that step?
So the fluid flow work is the closest to actually being done with a clinician, because that's the work with Professor Figueroa. And there's a whole lot of steps in terms of talking to a physician to make sure what you're doing is actually useful. And then if what you're doing is useful to them, you also have to get it through FDA approval. And of course, you need to do some sort of study, usually a retrospective study, where you look at patient data and you can show from retrospectively that your method worked compared to the physical measurement. So you take physical measurements of FFR, you have some sort of reduced order or surrogate model, and then you can say, look, I actually did predict this very well.